Welcome to the second half of the non-experimental designs lecture. You will find that non-experimental relationship designs fall into two types. Either the researcher is comparing two existing groups, for example, comparing their reading scores, or the researcher is trying to show a relationship between two variables, such as recess time and time on task. Let's look first at comparative design. These are usually quasi-experimental or ex post facto. Ex post facto simply means after the fact. It refers to the groups already existing. Let me give you an obvious example. In educational research, we often look at differences in poverty or differences in marginalized groups. It would be absurd to think that we would randomly assign children to high or low poverty or assign them to different cultural groups. In those cases, we want to compare what already exists. We always have to keep in mind other factors that would influence the outcome. For example, if I'm looking at a problem-solving program in 7th grade math and I compare 3 classrooms that use the program with 3 classrooms that don't, I need to make sure that the 6 classrooms are all roughly the same for ethnicity, math skill, teacher quality, etc. Sometimes I cannot do this. The classrooms I'm using are different. So I can statistically control for those other factors, and you will see that a lot in research articles. Let's look at some other examples. This is a very common type. Classroom A uses a math program, classroom B does not. So will the two groups have different means on their scores on the semester exam? This is a quasi-experimental. The groups already exist. The researcher isn't able to manipulate the IV because it's already there in the differences of the two classes. Sorry about that. So we're looking for differences in order to show a relationship rather than a cause. Comparative designs like this, they imply causation without the experimentation. So there's a fine line there. You will see researchers who try to say that this caused this, but they need to do it with caution unless they truly were experimenting and randomly assigning subjects to different groups. They're using the data that naturally happens and then reporting the effects of that. Good researchers, when they write it up, will call it a treatment or intervention group and a comparison group. It's technically not a control group, but you will see them call them that all times. It's important to look at the purposes of the designs when you're critiquing these. It would be, say you want to collect really good data on the quality of the programs and the fidelity of the programs. If you're going to compare 2 classrooms, you want to make sure that the teacher you think is doing an intervention really truly is doing the intervention. Now, when you have to critique an article like this, and I want you to be a really good consumer of research, look for a really solid description of the participants and the instruments that were used. Look for really rich description of the independent variable and the different levels of it. And even better if the researcher gives you how they went about identifying the different groups. Look that the researcher doesn't make any inference about causation, and look at the graphs really carefully. Let me give you 2 kind of fun examples. These are actual graphs that were used in 2 different newspapers about the increases in house prices this year. So the graph on the left was used under the headline of massive increase in house prices this year. And it kind of looks like it. But the graph on the right is the same graph, just with a different scale. And these came out of somewhere in England, if I remember correctly. So look at how the graphs are shown and the tables are shown in the research article. Here's another fun example. The class on the left, it looks like the students, there were huge differences in their scores. But if you look at the class on the right, the same scores, different scale. So be really cautious when you look at the graphs that researchers draw. Now, the correlational designs were described in the lecture under descriptive statistics. So I'm going to do a quick bit of review. Remember that correlational designs are used to describe a relationship between two variables. So that we call bivariate, or a combination of variables, and then it's multivariate. There's really no true distinction between the independent variable and the dependent variable in a correlational design. Usually the IV precedes the DV or predicts it, and there's a lot of common sense involved in that. Here's some examples. Scores on math achievement tests are usually associated. There's a relationship with the kids' attitude scores, and you could flip those around. It doesn't matter which one you use as your predictor. Now, some of them are more common sense. So is there a relationship between years of experience and teacher efficacy? Correlational designs can be used to predict. And when they do that, then you're drawing a trend line and you're using one of your variables as a predictor and the other one as an outcome or criterion. And there's usually, when predictions involved, there's usually a time interval. So 2 examples, parent education level can be used to predict reading comprehension in first graders. And yearly rainfall can actually be used to predict beef prices. You can imagine that if the rainfall goes down and farmers have to purchase hay from somewhere, the beef prices are going to go up. Prediction is another word for regression. And that's when we're actually putting in a trend line. So we're drawing a line that lets us predict, an imaginary line that lets us predict from the data points that we already have. So for example, in this one, when I put in my trend line, my regression line, I could extend that and then I could predict, if my data is good, I could predict the number of books read per year by 13 and 14-year-olds. When you're looking at correlation in research articles, look for the statistical significance and the alpha level that the researcher set. Basically, you're asking yourself, is the coefficient that R, Pearson's rho, is it statistically different from 0? And if the answer is yes, then there is a statistical relationship. So here's an example. In this case, the correlation is 0.35, which is low to low moderate. And then the researcher tells us that there's a 5% probability that this was simply due to chance and there's really not a relationship. So in this case, we say that correlation is statistically different from 0. Now here's an example when it's not. Same correlation coefficient, but because of the spread of the data and the data points that went into it, in this case, there's a 21% probability that this is simply due to chance rather than there actually being a relationship there. So it's not statistically significant. Multiple regression simply means that there's more than one predictor. And the predictors combine together. Somehow together, they all have different weights. And together they come up with a prediction that you can make. And it lets you statistically control for some of the variables. So you will see statements like, after controlling for SES, which is a very common one that we control for, we try to remove the effects of socioeconomic status so that we can get at the meat of what we're researching. Parent education level explained 26.4% of the variance in math achievement. Let me give you an example that has nothing to do with education, but will make sense to any of you who pay for car insurance. And if any of you have teenage boys driving, you will really get this one. With multiple regression designs, you can list out the variables that may influence an outcome. Then you statistically find a weight for each of those variables. So perhaps altogether, these factors account for 75% of the probability of having an accident. But which one of them is the most important? Well, of that 75%, maybe age is 15%, years of experience 52%, driver's ed 3%, gender 4%, and ethnicity 1%. Then the insurance company actually can base its rates on how long the person has been driving, their age, whether they've had driver's ed, etc. Now, my example has been incredibly simplified, but we often do this with multiple regression. We take a whole bunch of predictors and we try to predict or see what the relationship is or the weight each has on the score at the end of a test or something like that. So we try to say that these four contribute this much information and these contribute the other 74%. And you'll see this a lot in research. Now, when you're critiquing or consuming correlation, the number one thing to stay away from is causation. You never, ever, ever with correlation say that one thing caused another. One of the common examples that's used is smoking and lung cancer. There have never, ever, ever been experimental studies done on smoking leading to lung cancer. We've never assigned people to a smoking group and a non-smoking group. Most of the research that's come out of smoking and lung cancer is correlational. The reason that we're able to pretty confidently say that smoking leads in high percentages to lung cancer is that there's been so much correlational research done that it seems kind of obvious, and the scientific community pretty well accepts that. Correlations have to make sense, and you have to always be looking for some alternative explanation that could explain what's going on. I was reading an article where the state per pupil expenditure for education was negatively correlated with SAT scores. In other words, as states spent more on education per pupil, the SAT scores went down. And this doesn't make any sense if you just look at it that way. It's counterintuitive. There's something else going on there. Well, it turns out that you have to look at the percentage of the students who could have taken the SAT test who do. I'll use Utah as an example. In Utah, the SAT scores were very, very high, but their per pupil expenditures were relatively low compared to the rest of the nation. Well, it turns out that only 4% of the students who could actually take the SAT test in Utah. The ACT test is used more commonly for Utah universities. And so that 4% of kids who are taking the SAT test are actually kids who are trying to get into Ivy League schools back east or in Southern California. So it's just the top group of kids who even took the test. In that case, the other factors are just not making any sense at all of the correlation. Look at the sampling procedures that were used, and in other words, where did they find their groups, the variability of the scores. For good correlations, you want a real variety of scores so that you can see if there's really, really a trend there.